In this video, we're going to talk about matrix operations. First thing we'll do is just run through a few quick definitions related to matrices. So when we talk about the size of a matrix, we talk about the number of rows times the number of columns. And we always talk about the number of rows first. So for example, if someone gives you this matrix here, we would say that's a 2 by 3 matrix, or we say A is 2 by 3 because it has 2 rows and 3 columns. Occasionally we want to reference the entry of a matrix, so meaning we want to reference one of the numbers in the matrix. There are a couple of ways of doing that. So if your matrix is called capital A, you could reference an entry by using just the lowercase a and then writing the row and column index in the subscript. So this would mean the entry in row 2, column 3 of A. So row 2, column 3, that would be 6. Another way of doing it is just to use square brackets and then to write the name of your matrix in the square brackets, and then again in the subscript, just reference the row and column. Row 2, column 3 would be 6. Now there are 3 types of matrices that come up quite a lot throughout the course. So square matrix has size 2 by 2, 3 by 3, etc. So in other words, it's got same number of rows as columns. And then we have 2 specific cases of square matrices. So one is the identity matrix. We call that I, or sometimes I2 or I3 if we want to reference the size of the matrix. It's always square. And it has 1s along the main diagonal, 0s everywhere else. So the 3 by 3 identity matrix, 1s along the main diagonal, 0s everywhere else. And then another special square matrix is the diagonal matrix. So any real numbers we like along the main diagonal, off diagonal entries must be 0. So the identity matrix is a diagonal matrix, but a diagonal matrix is not necessarily going to be the identity matrix. So here we're going to practice some arithmetic operations with matrices. We've got 2 matrices given to us, and first thing we're going to do is find their sum. So notice that the matrices have the same size. They're both 2 by 3. The way we're going to add them together is we're just going to add the corresponding entries. So in the top left, we'd have 1 plus 1 is 2. Moving across the top row, we'd have 6 plus 0 is 6, and 1 minus 3 gives us negative 2. And so we're just going to continue that way, always adding the corresponding entries together. So in the bottom row, we'd have negative 1, positive 4, and then for the bottom right, 4 plus 9 is 13. The sum A plus B is undefined if A and B have different sizes. So part B, let's find 3 times A. So this process of multiplying a matrix times a number is called scalar multiplication. And that terminology might be familiar to us from vectors. We said when you multiply a vector times a number, that's called scalar multiplication. So we use that same terminology now that we're multiplying matrices by scalars. So what's going to be involved here, we're just going to go through our matrix A and multiply each of the entries by 3. So this would look like 3, 18, 3. And then in the bottom row, negative 6, and 12. So now we're going to try A minus 3B, and I've just recopied the matrices A and B here so that we can see them on the screen. So to do this, let's think of this as being A plus negative 3B. And so the first operation we would do is the scalar multiplication on B. So I'm just going to recopy the matrix A so that we've got that. And we're going to multiply B through by negative 3. So negative 3, 0, 9, negative 3, negative 18, negative 27. And then we can do our addition. So final answer is going to look like negative 2, 6, 10, negative 5, negative 20, and negative 23. So now let's make another definition. The transpose of a matrix A is going to be written A to the T, and it has rows and columns interchanged. Second definition, a matrix A is symmetric if A transpose is equal to the original matrix A. So when you're writing this symbol here, you can call it A to the T, or often we just call it A transpose. So the problem here is to find the transpose of the matrix. We're given our matrix A. So for the transpose, we're going to write A to the T. And what we're doing is we're just changing the roles of the rows and columns. So I think of it as, let's circle the rows of this matrix, and then let's recopy those into columns. So first row becomes the first column, second row becomes the second column, third row becomes the third column. So I'm just gonna circle the columns here so that we can see that in action. Now this particular matrix is symmetric. The way we know that, A transpose comes out the same as the original matrix. Okay, let's take a different matrix. Say B is 1, 2, 0, 6. Let's find the transpose of that. So just circle the rows of B, and those are going to become the columns of B transpose. So B transpose will look like 1, 2, 0, 6. If you like, you can circle the columns here just to emphasize what we did. And this matrix B is not symmetric because B transpose is not equal to the original matrix B. So now let's talk about matrix multiplication, meaning how to multiply two matrices together. So if you want to multiply A times B, what's going to be involved is calculating a whole bunch of dot products. So what's really important here is that we're talking about rows of the first matrix and columns of the second matrix, and we're somehow forming dot products of those things. Now, if we look in a little bit more detail at what we've got inside this matrix here, you can see that the particular row and column that we're choosing have to do with the position in the matrix. So when we're actually sitting in this position, which is row 1 and column 2, we're grabbing the first row of A and the second column of B. So you could say we're doing the dot product of the appropriate row and column, always taking rows of the first matrix and columns of the second matrix. So if we want to multiply these two matrices together, we're going to circle the rows of the first matrix, and we're going to circle all the columns of the second matrix, and we're going to be forming a bunch of dot products. So let's focus here on just the upper left corner here. This position is row 1, column 1. So we are going to take the first row of the first matrix with the first column of the second matrix. Now this looks a little weird because we're used to doing dot products where our vectors are, both sitting horizontally or both sitting vertically, but it's still the same familiar dot product. We just multiply the first two numbers together, so 1 times 1, and add on the product of the second pair of numbers. So overall that would give us 1. And as we move through this matrix, we're just adjusting what row and column we're using depending on our position in the matrix. So now if we're sitting here, that's row 1, column 2. So first row dotted with now the second column, dot product is 1 plus 8 is going to give us 9. And then finally in this position, we'd say, well, row 1, column 3 is the position that we're in. So take the first row, dot it with column 3 of the second matrix, you get 3 plus 24 is 27. All right, so now the way to speed this up is we're going to fill in the bottom row of this matrix by realizing, okay, we're going to be sticking with the second row of this first matrix and just now forming the various dot products with the columns. So a lot of people will just imagine sort of taking this vector and doing the various dot products, dot with that, dot with that, dot with that, and you can get pretty fast at this with a bit of practice. So first dot product would be -2, then we'd have 0, and then finally for the last one, another 0, because you got -6 plus 6 is 0. So now let's consider the sizes of these matrices. The first matrix was 2 by 2, and we multiplied that with a 2 by 3 matrix, and what that produced, I'm going to say equals because it produces a 2 by 3 matrix. So these inner numbers here must be equal. Otherwise, the product AB is undefined. So let's try to understand why that would be true. See, this number here represents the number of columns in your first matrix. So that's 2 in our example. And then this number here represents the number of rows in your second matrix. Because when we talk size, we're always saying rows by columns. Okay, so you need these two quantities to be the same so that you can form your dot product. See, if you had a different number of rows here than columns over here, you wouldn't be able to form that dot product. So saying that the inner numbers must be equal is just like saying you have to be able to calculate that dot product. And then if you look at the outer numbers, so meaning these two numbers, those give you the size of your product. So you can actually predict in advance what the size of your product AB will be. So just a quick example to illustrate this, let's say A is a 2x3 matrix and B is a 3x1 matrix. So if we think about the size of AB, we would say, well, we're taking a 2x3 times a 3x1. The inner numbers are equal, so that's good. That tells us the product will be defined. And the outer numbers will predict the size of the product. So AB will be 2x1. So that's what we're saying here. Now, if we do our multiplication in the other order, if we did B times A, that one's going to be undefined. So if you just think through it from a number point of view, size of B is 3x1, size of A is 2x3, and notice that these two numbers here are not equal. So that tells us right away, BA is going to be undefined. If you want to see a visual on that, we could draw a picture like this. So B is 3x1, meaning it's got 3 rows, but just a single column. So these dots here just represent some unknown numbers. And then our matrix A is 2x3. So it looks like that. Now, if you go and try to form your dot product, you're supposed to be taking the dot product of a row with a column. That's not going to work. Dot product is only defined when the two vectors have the same number of components. So that's why BA is undefined. So this picture here is representing the exact same idea as we're seeing here. It's just whether you want a visual approach or whether you want a numerical approach. So we actually figured out something quite deep in this example, which is that the order of multiplication matters. AB is a 2x1 matrix, whereas if we do the multiplication in the other order, BA is not even defined. So these are vastly different answers that we're getting from the two different orders of multiplication. So let's write that up as a fact, quite an important fact. AB is not going to equal BA in general. In other words, order matters when you're multiplying matrices. Let's do a bit more practice with our matrix multiplication. We're going to find BC and CB for the following two matrices. So let's think about BC first, and let's see if we can at least predict the size of it. So B is 3x2. Just write this on the side. C is 2x2. Inner numbers are equal, so that's great. And the outer numbers will predict the size of BC. So we know BC is going to be a 3x2 matrix, 3 rows, 2 columns. And we're going to circle the rows of the first matrix and the columns of the second matrix, and we'll form our dot products. So I'm going to take this first row 1, 2, and I'm going to dot it with the various columns. So with the first column, we get 1 plus 4 is 5. With the second column, -1 plus 8 is 7. Okay, then grab the second row of B. That's going to fill in the second row of our product. So our dot products are going to look like 3 plus 8 is 11, and -3 plus 16 is going to be 13. Okay, and then we get the bottom row just by grabbing the bottom row of B and doing the various dot products with the columns of C. So 5 plus 12 is 17, and then -5 plus 24 is 19. So there we go. Okay, now let's think about CB. First thing I would do is maybe just on the side, think about the sizes. So C is 2x2, B is 3x2. Already we can see the inner numbers are not equal, so CB is going to be undefined. If you want a visual way of thinking about that, C looks like this, whereas B looks like that. So when you try to form your first dot product, you'd be taking this row with that column, and there's a mismatch in the number of components there, so you can't form that dot product. So let's talk about why do we multiply like this, because matrix multiplication is quite strange. It feels very strange the first time you see it, and to some extent it continues to feel strange no matter how long you do it. But there's a very good reason why matrix multiplication is defined the way it is. So let's understand what that reason is. So let's imagine that you've got a matrix, little matrix of numbers, and you multiply that with a vector of variables, and you set that equal to some vector containing numbers. So if you actually multiply this out on the left side, you do your usual matrix multiplication. You'd be taking rows of the first matrix with any columns of the second matrix, doing your dot products. So you get things like x plus 2y and 3x plus 4y when you do that multiplication. And we're saying that's equal to the vector 5, 6. So if we then look at this component by component, what we'd be getting is an equation from each component. In other words, we're getting a system of equations. So the process of matrix multiplication really came from reverse engineering this process. 150, 200 years ago, when people were really interested in solving systems, they said, well, we want to take a system of equations like this, and we want a more concise way of representing it. So if we were to use matrices to do that, how would we have to define matrix multiplication to make this work? And so you can trace back through the logic here, and you can say, well, matrix multiplication would have to be defined in this sort of strange way, where we're taking dot products of the rows of the first matrix with columns of the second matrix. So what's going to be really useful for us is this way of representing a system of equations using matrices. So let's write this down as a fact. So a system of equations can be written in the form ax equal b, where A is our matrix of coefficients, x contains the variables for our system, and it's always written up as a column vector. So if you have 2 variables, x will look like this, or if you have 3 variables, it will look like x, y, z, always written as a column. And we have to insist on that just so that when we multiply A with x, that matrix multiplication is defined. And then on the right side, we have B, which is just a vector containing the constants from the right side of the system. And that is always written up as a column. Has to be a column just because it has to match the size of what we're getting on the left side. So we now have this really concise way of writing up a system of equations in matrix form. Just ax equal b represents that system. So main takeaway here is that matrix multiplication is designed to help us solve systems. So let's do a quick example here. Let's write the system in matrix form. When we say in matrix form, we mean we want it to have the form ax equal b. A represents the coefficients for our system. So 1, 2, 3, -8. X is the vector of variables, and it's always written in a column so that it can multiply with the matrix A. And then you have your vector of constants on the right side, always written as a column so that its size is the same as the size of what we have on the left side. So we're going to do a bit more practice with matrix multiplication. Let's say matrix A represents test marks for 2 students. Let's say they're Al and Bob, and we've got a test 1, test 2, and exam mark for each of them. And then matrix B contains the weightings of these various pieces of work. So both the tests are worth 20% of the final grade. Exam is worth 60% of the final grade. We're going to find Al and Bob's final grades, but the point is to use a matrix multiplication to do that. So we've already talked about how the sizes of the matrices have to be compatible when we're doing matrix multiplication. But if you're solving a real-world problem, you also need the categories to be compatible. So let's figure out what exactly we mean by that by working with these 2 matrices. So if we just reason through this from a size point of view, we would say, well, we can't multiply A times B like that. The sizes aren't compatible. We could multiply B times A. So we'd have a 1/3 matrix times a 3/2 matrix like that. So the sizes would be compatible. Now we need to convince ourselves that that's actually meaningful, and that's where the categories come into play. So the categories for B, I think I'll write this just a little bit bigger. Categories for B were test 1, test 2, and exam. I'll just write E for exam. And for matrix A, okay, we had the pieces of work in the rows. So the description of what work it was, test 1, test 2, exam. And then in the columns, we had the two students, Al and Bob. So I'll just write A and B. So when we say we want compatible categories, we mean when you form the dot product of a row with a column, you should be matching up the same categories as you form that dot product. So this looks right. T1 is going to multiply with T1, T2 is going to multiply with T2, E is going to multiply with E. And the reason that's important is because the numbers in here are the weightings that we want to multiply with the specific marks. So we're going to take a 1 by 3 times a 3 by 2. What we're going to produce is a 1 by 2. By doing this multiplication, the categories of test 1, test 2, and exam disappear. So by multiplying them with compatible categories, they've disappeared, and all we're left with is the categories from the columns of the second matrix. So we'll just have A and B. In other words, we're going to have Al's final grade and Bob's final grade by doing the dot product. So if you work out the actual numbers, it's 73 for Al and 70 for Bob. And if you did have multiple categories in the rows of the first matrix, you would see those multiple categories coming out in your answer. So again, practicing our matrix multiplication, let's find the second column of the following product. Well, we may want to predict the size in advance. So we've got a 3 by 2 times a 2 by 3. That's going to produce a 3 by 3 product. Now we're not interested in all the numbers, we just want the second column. So we need to think about where these numbers are going to come from. They're going to come from multiplying the second column here with the various rows of the first matrix. So you're always talking rows of the first matrix and columns of the second matrix. But this entry here, it's highlighted, is coming from row 1 with column 2. This one's coming from row 2, column 2, and this one's coming from row 3, column 2. So we're just figuring out which dot products we need to form. All right, so let's calculate those. So 1, 2 dotted with 2, 7 is going to give us 16. 2, 6 dotted with 2, 7, that's going to be 4 plus 42, 46. And then 2 plus 63 is 65. So there we've got our second column. So notice that there's a different way of thinking about this column that we just produced. This column is actually a linear combination of the columns of the first matrix. It's actually 2 times 1, 2, 1 plus 7 times 2, 6, 9. So the fact that we're trying to take away from this, the columns of the product AB are linear combinations of the columns of the first matrix A. And we're going to see this again in section 7.3. So we basically think about this here while we're on the topic of matrix multiplication. Now we're going to look at the idea of the outer product expansion of a product of matrices. So this is just a different way to think about multiplying matrices. It's a really specific technique that we're going to use at one point later on in the course. So again, it's one of these topics that we're sort of storing away for later on. So to do this outer product expansion, we're going to look at our first matrix. So imagine this is our first matrix here, and we're just going to break it down into columns. So in other words, just think of circling the columns of the first matrix, circling the rows of the second matrix. So I want to point out that this is strange. This is backwards to how we normally do our matrix multiplication. And then what the outer product expansion says is that to get your product, you can actually multiply the first column with the first row, and then add on the second column times the second row. Plus, you're doing this big sum, nth column times the nth row. And somehow that also gives you your product, AB. It's just a different way of calculating the product. So we'll do one example of that, and then we'll just store it away for later on in the course. So here are two matrices, A and B. We're going to find the outer product expansion of AB. And then what the outer product expansion tells us to do is multiply the first column with the first row and add on the second column with the second row. If you had 3 by 3 matrices here, then you would have 3 terms in this sum. Okay, and then let's see what happens when we do these multiplications. Now this thing here is a 2 by 1 matrix, which we're multiplying with a 1 by 2 matrix. So this is going to create a little 2 by 2 matrix for us. The thing is, the multiplication is quite easy because you've just got a single number in this row. So to say multiply this row with the various columns, it's just doing real number multiplication. There are no dot products involved here, in other words. So you multiply 1 by 1 is 1, 1 by 7, 7, and then in the bottom row, take the 0, multiply that through your vector, 0, 0. So you're just really doing the scalar multiplication of a vector. Okay, and then we're going to do the same thing over here. Again, we're going to have a 2 by 2 matrix. So multiply the 3 with that vector, you get 12, 6. Multiply the -2 with that vector, you get -8, -4. And then we sum the result. So 13, 13, -8, -4. Our usual way of multiplying, circle the rows of the first matrix, columns of the second matrix, and we're doing some dot products. So we would get 13, 13, -8, and -4. So I'm going to put a check mark here and say, yep, sure enough, that outer product expansion did give the correct answer. So now let's talk about the powers of a matrix. Suppose we have a matrix A. When we write A squared, we just mean multiply A by itself. So we'd be doing usual sort of matrix multiplication there. Just write out a copy of A, another copy of A, do your usual matrix multiplication. And the usual exponent rules apply. So the same exponent rules that you would use for variables. So if you multiply 2 powers of a matrix, the exponents are going to add. So you could say A cubed is A squared times A. Or you could say A cubed is A times A squared. And when you raise a quantity with an exponent to another exponent, the exponents multiply. So A to the 6 is the same thing as A cubed squared. Now we need one more fact before we can get into an example. Remember, when we write I, we mean the identity matrix. So if you're talking in a 2 by 2 context, it would look like this. Or if you were talking 3 by 3, 1's along the main diagonal, 0's everywhere else. So our fact says that if you take A times the identity matrix, you get A. And that's also true if you do it in the other order. I times A equals A for any matrix A. So to see that in action, if we took this matrix here, 1, 2, 3, 4, 5, 6, if we multiply by the identity matrix on the left, we'd have to have a 2 by 2 matrix sitting there. And you can check, yep, you do get this 1, 2, 3, 4, 5, 6 back again. If we put our matrix A here, and then we wanted the identity matrix on the right, we would need the 3 by 3 identity matrix to make the sizes compatible and confirm that that does really come out to the original matrix A. So we're going to simplify b to the power 2018, given that b cubed is equal to the identity matrix. Well, first thing we're going to do is we're going to think about what happens if we try to write 2018 as 3 times something plus something. So let's try some long division. We're going to divide 2018 by 3. So 3 divides into 20 6 times. 6 times 3 is 18, so that's how much we've accounted for it here. And we'll bring down the next number. Okay, so 3 divides into 21 7 times. That's perfect. That leaves us with nothing, and then we'll bring down the 8. So 3 divides into 8 twice. 2 times 3 gives us 6, so that's how much we've accounted for, and we've got a remainder of 2. So that helps us figure out what these numbers should be. We're saying 2018 is pretty much 3 times 672, but plus a remainder of 2. So that's going to help us quite a lot in simplifying b to the 2018. So now we can say b to the 2018 is b to the 3 times 672 plus 2, and we can think about using our exponent rules. So first exponent rule is that a sum in the exponent turns into a product. So b to the 3 times 672 times b squared. And then the other thing that happens is if you've got a product in your exponent, that's like an exponent raised to another exponent. So this is like b cubed to the power of 672 times b squared. Now remember what we were told in the question. We were told that b cubed is equal to the identity matrix. So what we've actually got here is the identity matrix raised to the power of 672 times b squared. Okay, now let's think about what happens when you multiply the identity matrix times the identity matrix. So that identity matrix times any matrix A gives us back that matrix A. So we should be getting the identity matrix here. Every time you multiply by the identity matrix, you should just get that identity matrix again. Therefore, identity matrix raised to any power is just going to give us the identity matrix. So that's going to be the trick to getting this simplified. So in other words, we've got the identity matrix times b squared, and identity matrix times any matrix just gives us that matrix. So the answer is b squared, and that's as simplified as it's going to get. Okay, let's look at a definition. We're going to let 0 represent the 0 matrix. So I'm purposely writing this with a bold 0 symbol so that it doesn't look like the number 0. The 0 matrix could have any size. So it could be 2 by 2, it could be 2 by 3, etc. So for our last problem, we're going to find a 2 by 2 matrix A so that A squared is equal to the 0 matrix, but A is not equal to the 0 matrix. So this is really going to test how well we've absorbed matrix multiplication. Let's think about what we're trying to do. So A is 2 by 2. We want to multiply A by itself so that we create a matrix just entirely of zeros. That's what the 0 matrix is. And by looking at the sizes here, we can figure out that the 0 matrix is going to be 2 by 2 because A was 2 by 2. All right, now we're not allowed to use the 0 matrix as our choice for A because that would be trivial. Obviously, if we multiplied the 0 matrix by itself, that would work. So what we're looking is for something non-zero. That's when you square it, you still get the 0 matrix. All right, now for these type of problems where you have to come up with an example of something, I would suggest trying to keep it really simple. So simple to me would mean maybe we can come up with a matrix that has zeros in 3 of the positions and let's say a 1 in the other position. So let's ask ourselves, would this work? No, that's not going to work. That does not equal the 0 matrix because the 1 is going to multiply with the 1. Okay, so let's come up with a different example. Can we move this 1 into another position so that when the multiplication happens, the 1 doesn't hit itself? Well, what if we put the 1 here? Remember, when we do matrix multiplication, we multiply the rows with the columns. See, that 1 is not going to hit itself. So that's going to work. So if we put zeros in these 3 positions, that's a pretty simple choice of matrix A. It's a non-zero matrix A, but when you square it, it does give you the 0 matrix. So the answer would be 0, 1, 0, 0. There are many other possible answers, but that's just one example. And I think it's a good way of testing whether we've really got that insight into matrix multiplication. So that's our video on matrix operations. Thanks for watching.